We should start.
Okay. So how many parts are there to chapter 12?
Many.
And that number would be?
2.
Well, today my plan is to go through these.
Okay.
Okay. So today we will start chapter 12. And chapter 12 is basically about formalisms and statistical mechanics. So I will introduce to you quantum statistics, classical statistics, fermions, bosons, all of the distributions that we have been talking about, and that for people who are going to be in quantum and modern next semester, that is the basis of where all of these things come from. Also, people who have taken modern and or quantum and or topics or are in topics right now, these are things you must have discussed. But this is where it all started. So we are going to talk about that. Ready? Okay, so what is the main goal of statistical mechanics? So the main goal of statistical mechanics was to find the link between too much detail at microscopic level and the phenomenon that is found in nature. So somehow we have to connect the microscopic world to the macroscopic things that we see around us, right? The big, huge things that we see. And the way statistical mechanics achieves that is by what is called the fundamental averaging postulate. Ready? So, in this case, is one of the very, very rare situations where quantum mechanics will come to help us instead of classical mechanics. So we do that by the help of quantum mechanics. So in quantum mechanics, a microstate is a quantum state of the whole ensemble that may be described by a single n-particle wave function. And that n-particle wave function, 1, contains all the possible information about the state of the system. So one wave function describes the entire state of the system. Now, do you remember what we actually called it? We called this gamma. And gamma was what? from last chapter? Started with an M. Excellent.
Wait, no, that's omega.
Oh, sorry, omega. My bad. It was omega. Multiplicity. Anyone remember what multiplicity was? The number of possible microstates that correspond to a single macrostate. Get it? Remember that picture? Okay, hold on. Do you remember that picture here? Do you remember this apartment picture? So can you tell me the probability that for each state, can I say that the probability of a microstate in this is exactly the same whether I look at this state, this state, this state, or that state? Because it has the same level, correct? What about here? There's only one state. If there was another one here, an apartment, will it have the same probability? The answer is yes. So, if I go back, may I say, in statistical mechanics now, may I say that my averaging postulate says all accessible microstates are equally probable? I want you to box that. It's going to be important. All microstates in a macrostate are equally probable, which leads us to different averages that we usually talk about. The time average and the ensemble average. Okay, what is a time average? So in order to do any measurement, we have to define a particular time at which that measurement is made. Okay? Can we make an experimental observation without giving a delta t? You have to have some time to make that observation. Okay? So all experimental observations or measurements need a delta t. Whether that delta t be 1 microsecond, 1 second, 1 hour, 1 year, 1,000 years, 100,000, doesn't matter. You have to have some time that you require. The problem in statistical mechanics is no matter what your delta t is, your system will have passed through many microstates. It will not stay the same. So no matter how small, how do I write this? no matter how large or small your delta T is, your system in statistical mechanics will have passed through many, many microstates. And our averaging postulate says that. So may I call this, what do you want to call this? Flower? What?
Butterfly.
Butterfly, okay. So our butterfly equation says, or postulate says, so my butterfly postulate says, what? All accessible microstates are equally probable. So what does that imply? I must have a time average over all microstates. Which implies we can replace a time average of one system by an instantaneous average over a large number of systems. Okay, now what does that mean? So I found this really cool example. How long are you guys on campus? Wait, what?
24/7.
Well, true. But over the course of your studies? 4 years. So I can do a time average of you for the 4 years and try to figure out exactly where you are at every given second. Or equivalently, I can replace you with a time average of the entire student body for an hour. Does that make sense? Okay, pay attention. So you're going to be here for 4 years. And I want to find out where you are, at any given time. Statistical mechanics says that I can, instead of keeping track of you, individual, for 4 years, I can equivalently take my entire student body, keep track of what every single student is doing over, say, 1 hour, and those two will be equal. That's called a time average. Make sense? So I just changed my delta T. So I make my delta T small or my delta T large, right? I could do a delta T large 4 years for one particle, see what that one does. Or I can look at my entire macro state for a short interval of time. Because I can't change I have to have a delta T for my measurement. And those two are equivalent. That's what this box means. That I can replace a time average of one system by an instantaneous average over a large number of systems. Okay. The second one, which is called the ensemble average, is also called a confession of ignorance. That is what we do in quantum mechanics. Isn't this fun? Now, what does it mean? It means since we do not know which particular microstate the system is in at time t, or time of interest, I can simply average equally over all possibilities. Basically, I don't care which state it's in, because I can equally average over all possibilities. And that is called the ensemble average. Now, what does it mean in simple terms? It means if I wait long enough, one particle state goes at least once through each of the allowed microstates. This is also called in quantum mechanics principle of equal a priori possibilities. What is an ensemble average? What it is that if you were to take a system of molecule, like a mole of gas, and you say, I want to study it at, say, this time, all possible states will exist in that system. And you can assume that if you wait long enough, each of those particles will go through each of those states at random. I don't know which one, but at any given time, I could look at it and I know that the system will be in one of those states at some time. If I look at one particle and I say I can either look at that particle through eternity, or I could look at the entire state for a short delta t, it will be equal. And that's where this butterfly probability is very, very, very important. All accessible microstates are equally probable. Okay, now the fun begins. We can also combine these both postulates and textbooks call this the quantum how do you pronounce this word? Ergodic hypothesis. So if you hear this, that's just a fancy word of combining postulates 1 and 2. What the quantum ergodic hypothesis say is combine postulate 1 and 2, the time average and the ensemble average, to state that the single isolated system of actual interest spends equal amounts of time given a long enough period in each of the available quantum states.